Okay, so I want to define a word for you. Okay, so the definition that I want to give you is a surface, and we may as well assume two-dimensional, and by two-dimensional here I don't mean living in two dimensions, I mean locally two dimensions. You guys understand what I mean by the difference there?
Yeah.
Wait.
For instance,
So it's like the top of a table.
this donut, right, is kind of two-dimensional. In that if you're standing anywhere upon that thing, there's a right and a left. You guys with me on this?
Okay.
Okay, so a surface, and by this I mean a two-dimensional surface, which might be a two-dimensional surface embedded in R6 or something, right, is orientable, and this is the word I'm defining. If there is a consistent choice of normal vector. What I mean by that is if you imagine a little fellow on this surface, a consistent choice of normal vector is that little fellow can wander around, right? But he'll always, if he comes back to where he started, he'll always still be standing on the same side. You guys see that? So a non-example of this, so this is an example, right? A torus. If you walk around this little donut, you're always going to be sitting on the outside, right? The glazed portion of the donut.
Okay.
You don't accidentally have this problem where you smear glaze on the donut and sometimes it's on the inside, right? And I know that seems stupid, but I put a marble in this, right? But this thing doesn't actually have an inside or an outside. You guys see this? Like the inside should be in here, right? But this marble is outside of it, and there is a consistent way, whoops, idiot. There is a consistent way for me to get inside from the outside without piercing the surface, right? So this Klein bottle has an inconsistent normal vector.
What do you just call that, a Klein bottle?
Yeah, this thing's called a Klein bottle. It's kind of, so this is actually a three-dimensional embedding of a Klein bottle, which is a little bit cheaty because this thing does actually pierce its surface right there. You guys all see that?
Yeah.
The full four-dimensional realization of this doesn't have that surface piercing property. So let's try the Mobius band that you guys each made, right? So you were writing your names around this thing, right?
Yeah.
And so if you imagine a little fellow standing where your first name was, right?
Okay.
So you circle that thing and think to yourself, okay, I am standing up on this side, right?
Oh, you want section?
So now I'm going to think about walking in the direction you wrote. So I'm going to walk, and 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 I'm going to walk. And eventually, right after you cross that tape section, your guy will be standing directly opposite of where that circled name is. You guys all see that?
Yep.
What does that mean about the Mobius band?
So you just went side, it's not
It's
oriented.
not orientable. It has one side, and it feels like it should have two because it's locally two-dimensional, right? Like there should be a kind of a top and a bottom, and this thing doesn't have that. You guys with me on this?
Okay.
So this Mobius band is not orientable, which is a problem for us when we're calculating this thing called flux integrals. So the idea of a flux integral, which is spelled this way, by the way, despite what it sounds like I'm saying. There's a coffee cup about this, but I'll let you guys figure that out on your own. So a flux is the amount of flow through an orientable surface. Surface. Okay, and the reason that I'm adding an orientable to this is that this won't make any sense if the surface isn't orientable because you don't know what through means. You guys all see that?
Okay.
Like I know what through a sphere looks like, right? Like I've got a sphere and there's some vector field going on, and maybe that vector field looks like this. So these ones are inside, and then out here they might be piercing the surface of the sphere, right?
Okay.
So through the sphere means from the inside to the outside there's some kind of flow going on.
Okay.
You guys see this? The kind of classic example of this is you have your very favorite river flowing downhill, as they tend to do.
But I found one for
Right? So here's your river. If you put a net in the river, how much water is flowing through this net?
All of it?
Yeah, all the water in the river is flowing through the net, right? What if you just put a littler net in there? Well, then you'll calculate some other slightly different thing. But the point is, through makes sense with that net because it has a consistent choice of normal vector. You guys see that?
Okay.
So when we talk about flux integrals, or fluxes in general, the very first thing you're going to do is say, is that thing orientable? If it's not, I can't even use the word flux there. It doesn't make any sense because the word through doesn't make any sense. You guys cool with that? You see how that is on the Mobius band, right?
Yeah.
Like, you don't know whether up is this way or that way, and so through just doesn't compute. Cool?
What was the word for that definition?
The word that I was defining?
Orientable.
I was defining orientable.
Definition of surface is orientable.
Yeah, so a surface is called orientable if there's a consistent choice of normal vector. Meaning that there's always kind of an up.
Is there a mathematical definition of consistent choice of normal vector?
Yeah.
Okay.
It really does kind of have to do with wandering around. So what that would mean is there isn't a path from point A back to point A where the normal vector would be different after following it around.
Which is like the definition of bonus vector.
Yeah, but I don't have a ton of, I don't have a tool for telling you how to walk around,
It's just
right?
any path you choose. Then yeah.
So there's a path, and then you push the normal vector around with these things called charts, and yeah, it gets to be a little bit tedious to write down, but it's pretty intuitive, right? Like,
Right.
if you as a little person could walk around on this thing and always have an up that made sense, then it's orientable. If you could walk around and find an up that was now down, then you would have a problem. This is a little bit like what's going on with the training thing.
I don't watch much TV.
You guys didn't watch Stranger Things.
I know what it is.
Okay, so the point of Stranger Things is that there's an extra dimension. They live in, so instead of you guys traditionally live in R3, right?
Yep.
Or at least you think you live in R3?
At the very least, our we perceive in our
Okay, so in Stranger Things, the people in the show live in R3, except there's an extra on and off dimension. Like, sometimes you're in regular R3, which would be your coordinate is whatever it is, comma 0. And sometimes you're in what they call upside down, which is regular R3, but then comma 1, where everything's all left up. You guys see this? Like,
Yeah.
this is sort of what extra dimensionality might mean. It literally just means you have to keep track of one more piece of information to decide where you are. You guys see this? Cool. So that's, again, a place that doesn't have a consistent choice of normal vector, because you can sometimes wander from the upside to the downside, to the upside down. Right side up to upside down? What do they call the normal one?
I think they just call it like that.
They just,
have a name
the
for
other
it.
one's just the
Yeah.
upside down.
Yeah.